So far up until this point, the only way for us to determine whether a sequence converges is by using the definition. While this is really good to know, it's not, we need some other tools to build up. Like if we don't necessarily have an explicit formula for the sequence, or we only know the sequence satisfies certain properties, we like to know some conditions on it that we could have to determine whether a sequence converges other than using the definition. And that brings us to the monotone convergence theorem. But first, a definition. A sequence a sub n is increasing if a sub n plus 1 is greater than or equal to a sub n for all n in the natural numbers. So if each successive term is larger than or the same size as the previous term, then the sequence is increasing. Similarly, a sequence is decreasing if each successive term is smaller than or the same size as the previous term. And we call the sequence monotone if it is either increasing or decreasing. So let's look at a few examples. Let's look at this first sequence. 1, 2, 3, 4, 5, 6, 7, 8. So this sequence right here is increasing. It's the wrong blue. It's this one. So this sequence right here is increasing. All right, each successive term is larger than the previous one. So this sequence is monotone. Let's look at the second sequence. -1, 1, -1, 1, -1, 1. So notice that the sequence is not increasing because this -1 is smaller than the previous term. But it's also not decreasing because this 1 is larger than the previous term. So this sequence is not monotone. All right, let's look at the third sequence. 1, 1/2, 1/3, so on. Well, each successive term is smaller than the previous one. So this sequence is decreasing. And therefore it is monotone. Finally, let's look at this last one. We just got a constant sequence of just zeros. 0, 0, 0, 0, 0, 0. We'll notice that each successive term is the exact same size as the previous term. And remember, when we defined increasing and decreasing, we use greater than or equal to and less than or equal to. So if each successive term is the same size or greater than the previous term, then it is increasing. So since each successive term is the same size as the previous term, this sequence is increasing. And by similar reasoning, it is also decreasing. So therefore, it is monotone. Now, a good question to ask is, does a monotone sequence necessarily converge? And the answer would be no, because this sequence right here, 1, 2, 3, 4, is monotone, but it does not converge. However, we can add one extra condition, that if a sequence, and that brings us to the monotone convergence theorem, which says that a sequence converges if it is both monotone and bounded. So let's look at this third sequence. This sequence is monotone, and it's also bounded. So, and we also know that this sequence converges too. This sequence converges to 0. So that kind of agrees with our theorem down here. Similarly, let's look at this fourth sequence. This sequence is monotone, and it's also bounded, and it converges to 0, which also agrees with our theorem. Let's draw a little picture that might give us a little bit better idea of what's going on here. So let's draw the number line. Okay, and we have a bounded sequence, so we can think of it as all the terms in the sequence are confined to a small area. And I guess the somewhat rationale behind this theorem is if you have a bunch of terms in a sequence where, okay, so from A1 I have to get larger or smaller. So we'll say I get larger every time. We have an increasing sequence where we have to stay the same size. So if each successive term must be larger than or the same size as the previous one, then eventually, right, I can't go left. All my terms are going to have to cluster up somewhere, and we're going to have to converge somewhere. So that's kind of the rationale behind this theorem. And let's give a formal proof. So we're going to start off with a monotone sequence that is bounded. So let AN be monotone and bounded. All right, now what does this mean? Well, because AN is monotone, we can say that AN is either increasing or decreasing. Now, we're just going to handle the increasing case because the decreasing case is almost identical. So we're going to assume, without loss of generality, that AN is increasing. So assume without loss of generality that our sequence AN is increasing. Okay, and what we're going to try to show is that the sequence AN is going to converge to the supremum of the sequence. Or kind of like somewhat like the maximum, the least upper bound. And to do that, we kind of need to consider the set of terms that contain A sub n. Like A sub n is a sequence, it's not necessarily a set. So we're going to let A, so let capital A be the set of all the terms in the sequence. Right, because if we want to show that the sequence A sub n converges to the supremum, then we can only take the supremum of a set. So this is the set of all the terms in the sequence. So we want to show that AN converges to the supremum of A. converges to the supremum of A. All right, let's show that. So let's scroll down a little bit. All right, let epsilon be greater than 0. All right, by one of our lemmas or theorems in the previous chapter, we can say then there exists a term in the sequence A sub capital N So we have some term in the sequence A sub capital N, right? So A is the set of all terms in the sequence, so its elements are terms in the sequence. So A sub capital N is just some term in the sequence. So let's specify that N is a natural number, such that the supremum of A minus epsilon is less than A sub n. This is by one of our lemmas in the previous chapter, that if we have the supremum of some set and we take, then if we subtract a little bit from it, then there will be some term in the sequence that will be greater than that, or some term in the set that will be greater than that. All right, now we're going to use the fact that an is increasing. So because let's write it. So because our sequence an is increasing, if n is greater than or equal to capital N, we have that the supremum of A minus epsilon is less than an. That's just what we had here, and that's what our lemma from the previous chapter said. Well, we know that because an is increasing, each successive term must be larger than or equal to the previous term. Okay, and we know that the supremum of A is an upper bound on this set A. So this must be less than or equal to the supremum of A. Okay, so we found a capital N in the natural numbers, where if all n are greater than or equal to capital N, then we have that A sub n is in the epsilon neighborhood of the supremum of A, which is what we wanted to show. So we can say that therefore the absolute value of an minus the supremum of A is less than epsilon. And I guess one way to make that one more clear, how we get from here to here, is we can, the supremum of A is less than the supremum of A plus epsilon. So A sub n is larger than the supremum of A minus epsilon, but less than the supremum of A plus epsilon. Okay, so we can say that an converges to the supremum of A. So consequently, the sequence an converges to the supremum of A. And that completes the proof. In the case where AN is decreasing, you can similarly show that the sequence AN converges to the infimum of A.